So up to now in our adventures on Poisson processes, we've considered only probability models and theoretical results. And all of the example calculations that we've done so far have been predicated on knowing the parameters of the process exactly. But we're statisticians, right? And the purpose of all of this is to model real-world data and answer real-world questions. Indeed, the word statistic quite literally means function of the data. So for today's lecture, we'll start looking at how one brings the data and the probability models together and then conduct inference. So the process of fitting models and then inferring properties of the true process or responses to questions about the true process under such models. So let's jump in. So for purposes of analyzing real-world processes, we need to fit mathematical models to observations we record from real-world data generating processes. So that is, we need to vet both the structure of the model, so is it a plausible representation of the data generating process, something we'll touch again on a bit later, and then also determine what its parameters are given the observed data. So for Poisson processes, that means determining the rate parameter given observed interarrival or arrival times and or counts in a given time window. So if we go back to our data table summary of the Poisson process components, the focal point of the analysis now becomes the entries in our data table and the parameters of our model. This is the domain of inference. And again, we distinguish between observational schemes as they naturally affect the construction of the likelihood of the data. Now, recalling that we conduct likelihood inference by evaluating the probability of observing a particular realization of the process, so in this case our data, under a given model specification, we seek to find that configuration. So that might be parameters and or structure or explanatory variables of the process, which is most likely to produce such a realization, i.e. that which we see. We thus encapsulate this in a mathematical statement as the estimate of the parameters of the process is given by that which maximizes the likelihood, or likelihood function, if you will, under a given model process. This invokes the maximum likelihood principle, which you should be familiar with from your adventures in statistical calculus. Now, how the likelihood function manifests in the present context is as follows. Assuming that we record the arrival times, and I'll just include a little footnote here that sometimes one just observes the counts, not the times, which necessitates a different construction of the likelihood, but for now we'll assume that you record the arrival times. Well, from that, we can construct the likelihood function for a Poisson process in terms of the observed interarrival times. Okay, so under our first observational scheme, which we refer to as fixed count mode, which you might recognize from our simulation schemes, we observe exactly n interarrivals to give us a data set, which I'll denote cal-d, of interarrival times t1, t2, all the way up to tn for that exact fixed n. Okay, and from that it follows that the density approximation to the likelihood of the data is given by the product of all for all I running from 1 to n of lambda times e to the minus lambda ti. Okay, so where that sort of kernel of the expression comes from the density of the associated with the interarrival times under our Poisson process, which is just the exponential distribution. Okay. Now that simplifies just to lambda to the power n times e to the minus lambda times the sum over all of the ti for I running from 1 to n. Okay, and as you may know already, since it's more convenient to maximize, we have then that the log likelihood function is just given by n log lambda minus lambda times the sum over all of the ti for I running from 1n. So the sum over all of the interarrival times. Cool, so nice, simple expression. Now, under the second configuration, which we'll refer to again as fixed window mode, where we observe or record observations over a fixed window of time, so again, say, running from 0 to b, we thus observe n star interarrivals, okay, to give us a data set, which again will denote cal-d, of t1, t2, all the way up to tn star now. Okay, where again that n star is now going to be random because we observe the process for a fixed window of time. We don't know how many observations we'll see. That n star is going to be random. Okay, and then we find that the density approximation to the likelihood function is as follows. It has two components. First component consists of the component that we'll recognize immediately. It's just, again, the product of the I running from 1 to n star, where again n star is now random, of lambda times e to the minus lambda ti. Okay, so the density, or the kernel, again, is given by the densities associated with the interarrivals that we observe over that window. Okay, and that's the first component of the likelihood. But then we take that and we post-multiply it, okay, with an additional probability, right, which is just e to the minus lambda times b minus Sn star, where Sn star is just the last arrival time in that window. Okay, now where this probability comes from is, well, it accounts for the fact that we don't see any observations in the window running from the last observation to the end of our window for which we observe the process. Okay, now again, remember that the likelihood function is just a statement about what is the probability of that which we observe. Okay, and in this case, that means what is the probability of observing n star events over a fixed window running from 0 to b, right? So we have to actually account for the fact that we don't see any additional arrivals apart from the last one in that last bit of time. Okay, and we can evaluate that probability straight from the Poisson probabilities under our model process. Cool. Now, as it happens, again, we simplify things. We write down the log likelihood function, and we'll see that it's given by n star times log lambda minus lambda times b. Okay, now you might look at that expression and say, well, hang on, where did the data go, right? Our data is supposedly the interarrival times, and indeed we see it in the likelihood function, but we also see that, well, they cancel out because the sum of the ti's is just the Sn star. They tend to cancel, they end up canceling out. And then we write down the log likelihood function, we see there's no longer any ti's. Okay, where did things go? Where's the information about that parameter lambda? Well, as it turns out, again, because n star is random, the information, okay, about lambda is contained both in n star and b, right? The parameter from the observational scheme that we fixed. Okay. Now, fortunately, both of these observational schemes permit analytical solutions for the maximum likelihood estimates. Okay, now what does it mean for something to be an analytical solution to the optimization problem? Well, that means we can write down an expression in terms of elementary functions. Now, sometimes, or more often than not, in statistics, we can't actually do that, right? So we'll have to then resort to numerical maximization of the likelihood function. That's, again, something we'll probably touch on later. But in this case, well, I guess in both of our observational schemes, we can actually write down the expression exactly. And indeed, we find that for the fixed count mode, we estimate lambda, so lambda hat, as just whatever that exact n is, divided by the sum over all of the ti for I running from 1 to n. Okay, it's a nice, neat, simple expression. Also, well, because this lambda hat is a statistic, it's a function of the data, it will exhibit some variation, so it will have a distribution associated with it. Well, as it turns out, we can evaluate the moments of that distribution, right, and interpret them. And what we find is that the expectation of that lambda hat under this observational scheme is n divided by n minus 1 times lambda, where lambda is, again, the true parameter of the process. We also find that its variance is n squared times lambda squared divided by n minus 1 squared times n minus 2. Okay, and then we see that, well, because the expectation of that lambda hat is not exactly the same as the true parameter, so lambda, we have a biased estimate of the true parameter, lambda. Now what that means is that, statistically speaking, it's always going to be slightly offset from the true value. And indeed, you see this a lot when you're dealing with count processes. For fixed window mode, okay, again, we maximize the likelihood analytically. We derive an expression, and we find lambda hat is now just n star divided by b. Okay, so again, the information is an n star and the window width that you have. And then we find that the expectation of that estimate, so lambda hat is just lambda, so the true parameter, so it's an unbiased estimate. And then also its variance is given by lambda divided by b. Okay, now what's cool about this variance estimate, it's nice and easy to interpret. Now remember, we're trying to estimate lambda. We don't know what it is. It's some value, we don't have any control of it. Okay, But looking at that variance, we see that, well, it's a function of b, the window width. Okay, so if we want to improve our precision of our estimate of lambda, whatever lambda may be, well, if we just increase our window width, then lower its variance, so we get more precision. Okay, so nice and easy to interpret. Cool. So now we have two simple estimators for their respective observational schemes, and if I give you some real-world observations, you can now use these to estimate the rate parameter of a Poisson process model for such data. Furthermore, you can now use this to estimate the rate parameter to perform calculations like we have done in our examples up to now, provided, of course, that it's a plausible model and that you understand how to account for the uncertainty around the estimate of the rate parameter. So I'll include a little interesting question in the homework problems, which hopes to illustrate this last point, but we'll probably touch on that again in other videos on inference. Cool, so let's look at some example problems. Okay, so consider the following timesheet where we record in minutes how long it takes for the first 6 runners to arrive after the 3-hour mark of the Himmel en Aarde marathon that we ran in 2020. Okay, so note that we're not looking at the first runners to cross the finish line. We say that we're going to start recording at the 3-hour time, and then we're going to wait for the first 6 runners after that point in time to arrive. And then we're going to write down the times. Okay? And then specifically what I've done then is I've populated your little data table here, and I've populated in terms of minutes. Okay, so you'll see that the first arrival after the 3-hour mark took 2.050 minutes. Okay, so that's a scalar value. That doesn't mean like 2 minutes and 5 seconds. It's 2.050 minutes, etc. Okay, so we write down the times for the after that point for the first 6 runners. We calculate the inter-arrival times, and now we are presented with a bunch of questions. Okay, question 1. Assuming that it adequately approximates the observed process, estimate the rate parameter of a Poisson process model for this data. Okay. Right, so this is an easy one. Let's tackle it quickly. Okay, so we're clearly using the fixed count observational scheme. Why is that? I've told you that we're going to wait until we see the first 6 runners. Okay, so I've fixed the n there. Okay, so that means that we estimate lambda, so lambda hat, as being n divided by the sum over all of the t's i's. Okay, and then we calculate that as 6 divided by 7.033. Where did that 7.033 come from? Sum of all the inter-arrivals, which also happens to be the last arrival time. And then we estimate that as 0.853 runners per minute. Okay, so that's our estimate of the rate parameter for the process. Now, obviously, we're cognizant of the fact that this estimate is subject to some variation, and we've only used 6 observations, so we need to get some idea of the certainty with which we've pinned down the rate parameter of the process, presuming, of course, that it's an appropriate model. And that leads us to question 2. Give an exact 90% confidence interval for lambda. Okay, now it states exact 90% confidence interval. Now, from your likelihood theory knowledge, you will probably know how to construct a confidence interval which is approximate, but here it asks for an exact confidence interval. Okay, and well, for this we'll actually need an interim result, and the interim result is as follows. Okay, so let x1, x2, all the way up to xn be n independent identically distributed exponential lambda random variables. Okay, then we construct a new random variable, which is just 2 times lambda times the sum over all of the xi's. Then that random variable must be distributed as chi-squared with 2n degrees of freedom. Again, that's convenient because, well, we can construct a exact 90% confidence interval using the following expression. What we do is we say, take the probability that that random variable falls between 2 points and set it equal to 0.9. Okay, so we get a 90% interval. Okay, and then what are the 2 points that we can use? Well, we know what the distribution of this random variable is. Well, why don't we just read off the 0.05 and 0.95 quantiles, okay, to give us the endpoints of that interval. Okay, so we take those quantiles from the chi-squared 2n distribution. Okay, and now what we can do is we can manipulate this expression to make a statement about lambda. Now note here that there's no lambda hat in this statement. Okay. Recall that the confidence interval is the statement about the true parameter, lambda. Okay. Now the data used in the estimate, or the estimate itself, may still feature in the calculation of the interval, but ultimately it's just a statement about lambda. Okay, so we're going to take this expression and we're going to manipulate it in a way to make a statement about lambda, the true underlying parameter. Cool. So we go back to our calculation and then we note that, okay, well, for these purposes, for our particular application, we need to evaluate the 0.05 and 0.95 quantiles of the chi-squared distribution with 12 degrees of freedom. Okay, so 2 times 6. So in R, we go calculate that as q chi-squared. We give the probabilities and the degrees of freedom, and we read those off as 5.22 and 21.03 roughly. Cool. Now we go back to our expression and we say, okay, well, that means take the expression, the probability that 2 lambda times the sum over all of the TIs falls between 5.22 and 21.03, and set that equal to 0.9. Okay, now we can manipulate that expression to make a statement about lambda. And indeed, when we take the 2 and sum over TIs, take it over to the other side, divide by that, that gives us our confidence limits, right? And indeed, we see then that a exact 90% confidence interval for lambda, so the true parameter, is 0.372 to 0.1495. Okay. Now, if we look at our estimate of lambda, so lambda hat is 0.85, and we look at that interval, we can actually see, well, based on the magnitudes here, that's actually quite a bit of variation, right? So we're not quite as certain about what that value is, but again, that might just be a function of the data, right? We've only got 6 observations here, so perhaps not unexpected. Cool, so I hope you found that interesting. There's actually quite a lot more that can be said about conducting inference under Poisson process models, but we'll leave it at that for now. As usual, I'll leave some problems on screen for you to check out, and then I'll see you in the next one.